We had 4 questions for homework on page 486 last night. We're going to go over 3 of them today, questions 6, 7, and 9, starting with question number 6. Let's start off with number 6 here. It says a student sitting in a chair with a nearly frictionless rollers here. Her homework bag is in identical chair right beside her. By the way, why is it talking about frictionless rollers here? What are they kind of hinting at right there? Yeah, that it's an isolated system, right? There's no external forces acting here. Her homework bag is in an identical chair right beside her. The chair and bag have a combined mass of 20 kilograms. The student in her chair have a combined mass of 65 kilograms. She pushes her homework bag away from her. I don't know why you'd want to do that, because Friday night tonight, and get your homework beside you, don't you want to do it? Get it done with, right, on a Friday night? 0.6 meters per second relative to the floor. What's the student's velocity immediately after the interaction? This is like, it's like an explosion, right? Not a collision per se, but an explosion. Not literally. Okay, you don't have literally something blowing up, but you do have basically a student in a chair and a bag in a chair that are together. And then when the student pushes it away, they separate and they become 2 objects, right? 2 separate objects. Let's write down some givens here. We know it's going to be conservation of momentum. The total momentum of this system is going to remain the same. Hey, what's the total momentum to start off? Peter? It's 0, right? Givens here. Let's say the mass of the student in the chair is, did it say? 65 kilograms. Let's say the mass of the bag in the chair have a mass of 20 kilograms. VI is 0, right? Nothing's moving to start off. She pushes her homework bag away from her at 0.6. That means V2F is going to be 0.060 meters per second. That's how fast the homework bag and the chair move away, 0.06 meters per second. What's the student's velocity immediately after? We're looking for V1F. So we're going to say PI equals PF. We're going to say, usually we say MVI because there's one object, but it has no momentum to start off because it's at rest. So let's just say 0. 0 momentum is equal to M1 V1F plus M2 V2F. We have to include our 2 terms afterwards because we have 2 objects afterwards, right? The one object that wasn't moving, that has no momentum, is split up into 2 objects that both have momentum. Mass 1 is 65 kilograms. V1F is what we're looking for. Mass 2 is 20 kilograms times V2F is 0.060 meters per second. So let's pull the calculator out to solve this one here. Make sure we can all do it. We're going to say 20, actually we're going to say negative 20 times 0.06. How come negative 20? Why negative 20, not 20 there, Rosie? You got, one's going to be positive, one's negative, but I wrote that down as positive. Yeah, I'm moving it to the other side. Now, I defined the backpack and the chair moving away as positive, so therefore the velocity of you and your chair is going to be negative, right? You could have easily defined it the other way around. Yeah, that would be fine. One's got to be positive, one's got to be negative for sure. But since I made that positive, I'm switching it to negative as I pull it over to the left-hand side by subtracting. So it becomes negative 1.2 divided by 65. We get a pretty small number there, right? 0.018. That seem reasonable? Yeah, you're going to be going pretty slow, right? You're sitting there, you push your backpack away from you. How fast are you going to go back? Like hardly at all, right? Because you're heavier. You're a lot heavier than the backpack is. Okay, question 7. At airlift, the space shuttle has a mass of 2.04 times 10 to the 6 kilograms, which is pretty heavy. Rocket engines expel 3,700 kilograms of exhaust gas during the first second of liftoff. And you got to figure that's got to be expensive to go fill up that puppy at Shell. And that's going to cost you a lot. If it's expelling 3,700 kilograms of exhaust gas in the first second of liftoff. Yeah, I don't even know. Pretty sure you can't fill up the space shuttle at Shell. I don't know how much the fuel costs, but I have a feeling it's not 88 cents a liter either. Gives it a velocity of 5.7 meters per second upwards. What's the velocity of the exhaust gas leaving the rocket engines? They're telling us to ignore the change in mass due to the fuel being consumed. The reality is, as this rocket takes off, it will be lighter afterwards than before, right? Because it loses fuel. The good news is the shuttle has a mass of 10 to the 6 kilograms. The fuel is only a small fraction of that mass. So what they're saying here is that the fuel is such a small fraction of the mass that it doesn't really matter that that mass is no longer there. It's not going to affect things dramatically. Now, if you're a rocket scientist and you're calculating this, well, then you're going to take that into account, right? Because you want to be perfect right on. But for us, we're going to get an answer that's very, very good without worrying about the loss in mass. The other issue here, and we can't deal with this because it requires more sophisticated mathematics than we have. But the other issue is that this is not technically a simple explosion like, like the last question was, where you push the chair with the backpack away from us. Okay, this is an explosion where one object becomes two objects, right? The shuttle and the fuel become together, the shuttle goes one way and the exhaust gas goes the other way. Sounds the same, except that the exhaust gas doesn't all go out at one time, right? It goes out over a period of time. So that becomes technically much more complicated to deal with. We won't have to be able to deal with that in Physics 30. So we're going to pretend that it all goes out as one burst, which it doesn't really, right? But it goes out in 1 second. So it's close enough that we can do that and get a pretty reasonable answer here. So what do we got here? We're going to say the shuttle has a mass of 2.04 times 10 to the 6 kilograms. And we're going to say that the exhaust gas, we're going to call that M2, is 3.7 times 10 to the 3 kilograms. We're going to say that VI is equal to 0 because you guys have seen shuttle launches before. Sitting on the launch pad, 0 velocity. The rocket is given a velocity of 5.7 upwards. So we're going to say V1F, the shuttle, the rocket, is going at 5.7 after 1 second, 5.7 meters per second upwards. We want to know the velocity of the exhaust gas coming out the back. We want to know what V2F is. So we're going to say again that PI is equal to PF. It's an explosion. The initial momentum is 0. The final is M1V1F plus M2V2F, the rocket and the exhaust gas. Even though this is, as we say, a bit of a simplification in two fronts. Mass 1, the shuttle, well, the shuttle actually weighs a little bit less than this now because the exhaust gas went out. But to 2 decimal places, it's still the same. So we're ignoring the loss of exhaust gas. We're looking for, sorry, we have V1F, it's 5.7. The mass of the exhaust gas is 3,700. And the velocity of the exhaust gas is what we're looking for. What would you expect the velocity of the exhaust gas to be? Big or small? Ollie? Why? The exhaust gas isn't a bigger mass. It's only 3,700 kilograms. The shuttle is 2.04 times 10 to the 6, like 2 million kilograms. And the exhaust gas is 3,700. Ethan? Yeah. So the momentum is going to be the same of the exhaust gas and the shuttle because the total initial is 0, the total final has to be 0. The shuttle's going one way, has positive momentum. The exhaust gas goes the other way, has a negative but equal in magnitude momentum. But it weighs a lot less. Since it has the same momentum and has a lot less mass, then it's going to be a lot faster moving. So let's figure that out. Multiply these together, take it to the other side by subtracting, divide by 3,700. And what do we end up getting there? Somebody got it? Yep. 3,142.7 meters per second, or we're going to round that to 3.1 times 10 to the 3 meters per second. 3,000 meters per second is absurdly fast. Yeah, it's Mach 10, almost Mach 10. Almost 10 times the speed of sound. Good. So when you go home tonight and mom and dad ask you what you did at school today, say, like, Mom, it was really nothing, just a little rocket science. It's not like it's rocket science. Wait a second, it is. Number 9, a hockey forward with a mass of 95 kilograms skates in front of the net at 2.3 meters per second to the east. He is met by a 104-kilogram defenseman skating at 1.2 to the west. What's the velocity of the resulting tangle of players if they stay together immediately after impact? So they're tangled together, or they're just hugging each other. But this thing is one object regardless. This is a collision. Conservation of momentum applies. We could do impulse again, but we'd have to pick one object or the other and not both. Whenever you have information about both, let's do conservation of momentum. We're going to say that M1 is 95 kilograms. We're going to say that his velocity, V1I, or her velocity, V1I is 2.3 meters per second. I guess it's a he, yeah. He's met by a 104-kilogram defenseman. That's going to be M2, traveling with a velocity of V2I at negative 1.2 meters per second. I should have circled that, right? Draw attention to it to remind me that it's to the west. I didn't forget, I remembered, but my chances of forgetting are greater if I don't draw attention to it. What's the velocity of the resulting tangle of players? Sounds like they stick together. We're looking for VF, the combined. So let's say PI equals PF. We got two objects before. And we have one object afterwards, right? MVF. They stick together. M1, 95 times 2.3 plus 104 times negative 1.2. Combined mass would be 199 times VF. So let's get this number, add it to this number, but make sure you add a negative value because of the negative 1.2, and then divide it by 199. What do you end up getting there? It could be a big number or a small number. Rosie, big or small? It'll be small because you got more mass, right? Same momentum, more mass now. Rosie, what is the value there? 4.7? And we get a positive value there, which means it's to the east, right? Good. Yesterday, we introduced a new scenario of collisions, a collision in which we had two objects going at right angles to each other as opposed to on the same plane or on the same axis. We introduced it like this. We said we had one object moving towards a stationary second object. They collide, they stick together, and they go off as one object after the collision takes place. This would be their velocity after the collision takes place, right? But then we had another one where we had object number 1 at rest instead of object number 2. Object 2 moving downwards towards object number 1 with a certain velocity. They stick together, head off as one object, and their final velocity would look like this. We know how to solve both of these problems. This problem would be solved using PI equals PF. Specifically, we'd say M1 V1I plus 0, because the second object doesn't have any velocity. Equals, if they stick together, we would say M times VF, M being the total mass. Put a little subscript T there if you want, doesn't really matter, times the final velocity, right? We'd solve for that final velocity. We don't have any numbers, so we can't solve for it in this case, but you can see how we could easily solve for that final velocity. Done deal. We've done that 20 times so far, I bet. We had a quiz on that on yesterday, and you guys did fine on that quiz. Let's look at the other scenario here. This time it would be, again, PI equals PF, but this time we're going to say 0 for object number 1 plus the momentum of object number 2, M2 V2F, equals the final momentum of the combined mass, which is M times VF. Once again, we'd solve for VF if we had numbers. and get a value. We can do that. We've done that 100 times. Okay, we know how to solve for that final velocity in the first case and in the second case. But what if we have a scenario like this? What if object number 1 is moving to the right, just like it was in the first diagram? Object number 2 is moving downwards, just like it is in the second diagram. They stick together when they collide. When they do that, they're going to go off somewhere down here. So how do we analyze this? Well, it doesn't have to be any harder than what we just already did. We're going to say it has two components, an x and a y component. Whenever you're dealing with a problem that is not just on one axis, that has some part of the question on one axis, part on another axis, then you've got to break it now into components. The x component could be described like this. Pi equals Pf. M1 V1I plus 0 equals MVF. Exactly like problem number 1 up here above. Why is the second momentum still 0, even though clearly in this third diagram it's moving downwards? Why am I saying it's 0? Get it right, because we're analyzing the x-axis, and object number 2, although it is moving on the y-axis. We're only paying attention to x right now, so we're going to drop everything that's not on x. It becomes the exact same problem as that first one I showed you. You could solve for VF here the same way as you did, same way as you would have in this problem. Now let's do the y-axis, the y components. Pi equals Pf again. This time we'd say 0 plus M2 V2I equals MVF. Why do we say the momentum of object number 1 is 0 now? Because what? Because it's not moving on the y-axis. It's moving, but it's only on the x-axis. We pay attention to object number 1 when we're analyzing x, and we pay attention to object 2 when we're analyzing y. Now, we have to include the total mass here for both x and y, because you can see the resulting velocity from the combined wreckage here is on both the x and the y-axis. It's down at some angle, right? So we have to include that for both x and y. This is exactly like the second diagram and analysis we did right up here. If you can do this, then you can do this. If you can do this, then you can do this. However, there is still a little bit more to do. Man, already one question is as much work as 2 questions was before. But we're still not done. What are you going to do next? What's the third part of this question after x and y? Ollie?
I don't know how to say it, but for a lot of
R, the resultant vector? Okay, how do you find the resultant vector typically? Yeah, draw a triangle and do the Pythagorean theorem. So what we're going to do is redraw this. VF for the x component is going to be like this. VF for the y component is going to be like this. And then we're going to join the start to the finish with the resultant vector or the hypotenuse, and we're going to find its value. We can do that easily, right? By using the Pythagorean theorem. The magnitude of the resultant vector, which is the final speed, is the square root of a squared plus b squared. Or the square root of the final velocity x squared plus final velocity y squared. Right, Adele? And then, of course, we can find that angle as well. We are talking about a resultant vector, a final velocity. So we're going to say theta is equal to the inverse tan function of opposite over adjacent. So if this is A and this is B, we're going to say B over A. Or, you know what? Let's make it, let's change this as well, actually. From A squared plus B squared, x squared plus y squared. Right? Look at what we've just done. Look at what we've done today and yesterday. We've solved this problem. We've solved this problem. And we've solved a problem that we did last year in Physics 20. So really what we see here now, which seems to us as a new problem, it really isn't a new problem at all. It's just a combination of 3 problems that we've already done between this year and last year in Physics 20. Here's the summary in words of what we've just done. All right, let's have a look at an example on page 492. It says a 90 kilogram quarterback moving at 7 meters per second. I don't know why the book uses this notation. Our diploma exam and our unit test do not use this notation. 7 meters per second means it's going this way. Okay? That doesn't mean south. It just means from whatever we define as our positive x-axis, it's going, this would be 0 degrees. That would be 270. So we got our first object, we'll call it object number 1, our quarterback moving this way, has a mass of 90 kilograms, moving at 7.0 meters per second. We got a 110 kilogram linebacker running at 0 degrees, like this. Again, don't lose any sleep over that notation. Okay, usually something like this would be drawn out for you. It's the velocity of the center of mass of the combination of the 2 players immediately after impact. So these 2 players maybe combine, they embrace and head off as one, or maybe they don't, maybe they go off like this, but the center of mass of them, which is where if they did embrace and go off as one, goes off down here somewhere between the 2 of them. So how do we do this? Well, clearly we have 2 axes. Some of it's on x, some of it's on y. So let's do conservation of momentum, but let's break it up into x component and y component. We're going to say pi equals pf for both of them. m1 v1i plus m2 v2i, but what's v2i? 0. It's on the y-axis. We're analyzing just the x. Equals mvf. m1 is 110 times 8. Equals 200 kilograms times VF. So we've got 110 times 8 is 880 divided by 200. I think it's 4.4. Is that right? 4.4 meters per second. Let's do the Y component now. Once again, PI equals PF. This time we would say 0 plus M2 V2I. Why 0 here for object number 1? It's moving at 8 meters per second. It's moving faster than the other one is. Why are we ignoring it? Because it's on the x-axis, and we're analyzing the y-axis now. One at a time, either x or y. M2 is 90 times V2I is 7.0. Actually, we make that negative 7 because it's downwards, right? Equals total mass is 200 times VF. 90 times 7 is 630. Negative 630 divided by 2 would be 3.15. Thank you. Negative 3.15 meters per second. Now, let's put them both together. We have 4.4 to the right. We have 3.15 downwards, and our resultant velocity is going to be right here. We're going to say V is equal to the square root of 4.4 squared plus 3.15 squared, and we're going to say theta, always drawn at the start of the vector diagram, is equal to the inverse tan of opposite over adjacent. Let's say this side of the room, first 3 rows, we're going to calculate V with the calculators, and then these 3 rows, your task is to calculate theta with your calculator. No one's calculated theta, which is 35 degrees. Now, what do you get? 35.536, so it would be 36 degrees then, right? 36 degrees, good. Now, had we drawn it the other way, y then x, we would have gotten what? It would have been 54 degrees, right? Which would have been correct, according to the diagram that you had drawn. What's v work going to be? Yep. Good, done. Is this harder than the questions you've been working on thus far? No, I don't think so. Is it more work? Definitely. It's 3 times the amount of work, right? It's an x problem, it's a y problem, and then it's a trigonometry problem down here. But it's still harder. It's just more work. And more work, of course, leads to more chance of making a silly mistake, but if you're careful, you can still do these. Yep. That's a good question. In this question, I'm not putting a direction there like a south of east type thing. That's what you're thinking of, right? The reason I'm not doing that is because their frame of reference is that 0, 90, 180, 270 degree frame of reference. And you haven't learned that, and I'm not going to teach you that other than, you know, drawing the picture for you. So we're going to leave that off right now and just say, look, I have my diagram labeled, so I know where it's going, right? But if you've got a north, south, east, west frame of reference, then yeah, then you'd want to say 36 degrees south of east or whatever the case may be. All right? All right, we got a couple minutes to work on our homework questions on page 492. Let me just help you out a little bit with question number 1. Okay, let me draw the diagram for you. It says traveling at 90 degrees. That's this way. 90 degrees is this way. The other one's traveling at 180 degrees. 180 is this way. So they're going to collide like this. They stick together, so they're going to go off as one object like this. And question number 2 uses north, south, east, west, and you guys are familiar with that one already.